Good day, everyone. In this video, we are going to discuss the notion of proofs and how to describe methods for constructing proof. So what is a proof? A proof is a valid no argument that establishes the truth of a mathematical statement. So in the previous lecture, we proved statements involving propositions and quantified statements. So using a set of premises as well as rules of quantifiers, we arrived at some conclusion, okay? Or we wanted to prove that the statement or the last statement is correct given some premises or evidences. So in this kind of proving, also steps were supplied and the rules for each step in the argument were given. So these are called formal na proof. However, these are very tedious to do. So it is extremely long and hard to follow. So especially if we have plenty of premises, we have plenty of evidences. Okay, so the number of steps as well as the number of rules will be plenty, and it will also be prone to errors. So in practice, the proof of theorems designed for human consumption are almost always informal na proof, wherein more than one rule of inference may be used in each step, or there are some steps that we may skip, and there are some axioms that we may assume, and there are rules of inferences that are not explicitly stated. So we will be defining axioms later on, right? So proofs are discussed in this chapter are very important, not only because they are used to prove mathematical theorems, but there are also a lot of applications to computer science. So this include verifying computer programs are correct and establishing that operating systems are secure, making inferences in artificial intelligence, showing that system specifications are consistent, and so on. So consequently, understanding the techniques used in proofs is essential both in mathematics and in computer science. So formally, a theorem is a statement that can be shown to be true. So in mathematical writing, the term theorem is usually reserved for a statement that is considered at least somewhat important. So in order for us to demonstrate that these theorems are true or valid, then we can use proof. So a proof establishes the truth of the theorem. And the statements that we can use in the proof are called axioms, lemma, corollary, as well as conjecture. So when we say axioms, these are statements which we assume to be true. Okay? The axioms may be used using primitive terms that do not require definition, but all other terms used in theorems and their proofs must be defined. So also lemma. Lemma, on the other hand, is a less important theorem that is helpful in the proof of other results. So complicated proof are usually easier to understand when they are proved using a series of lemmas. However, each of these lemma in the series must be proved individually. The corollary, on the other hand, is theorem that can be established directly from a theorem that has already been proven. So the conjecture, on the other hand, is a statement that is believed to be true for which there is not a proof yet. If the conjecture is proved to be true, then it becomes a theorem. So a conjecture is a statement that is proposed to be a true statement, usually on the basis of some partial evidence, a heuristic argument, or some intuition of an expert. So if we can prove that this conjecture is true, then it becomes a theorem. However, many times conjectures are shown to be false, so they are not theorems. So here's a diagram on how we can understand it. So in order for us to prove that a certain theorem is true, so we can use some proof, okay? And this proof may be axioms, lemma, or conjecture. So axioms are statements which are given and for which we assume to be true, while the lemma are the result that needs to be proved to prove the theorem. So these are less important na theorems. Okay, and this lemma must be proven as well. While a conjecture is a guess or a hypothesis that may be done by an expert or may be resulted from a partial evidence. Okay, and this lemma, as I said, is a pre-theorem result that needs to be proved to prove the theorem. So we can also use some axioms or conjecture in order to prove the series of lemma. Okay, and from theorems as well as axioms, and then we can form more theorems. Since this theorem is already proven, then we can use that as a proof to prove this more theorems. While a corollary is a post-theorem result which follows easily from the theorem that has already been proven. In other words, this is a result or result of proving certain theorems. Okay, so since these are already proven, so there are some corollaries that are also proven. And again, if we want to prove that a statement is true, we can use proof like hypothesis of a theorem or the axioms that are proven to be true and previously proven theorems. With these ingredients as well as the rules of inference, then we can deduce the truth of a certain statement. So before we introduce methods for proving theorems, we need to understand how mathematical theorems are stated. So many theorems assert that a property holds for all elements in a domain. In other words, what we mean is a universal generalization, such as integers or the real numbers. Although the precise statement of such theorems need to include a universal quantifier, which is a standard na convention in mathematics. So for example, if we have a statement, if x is greater than y, where x and y are positive real numbers, then x squared is greater than y squared. So this is a theorem that holds for all elements in the domain positive real numbers. So what this really means is that for all positive real numbers x and y, if x is greater than y, then x squared is greater than y squared. So as you can see, we omitted the universal generalization for all. Okay, so we can state it using this in predicate form. For all x and for all y, r of xy implies s of xy, where x and y are members of or elements of all positive real numbers r. Okay, such that r of xy states that x is greater than y, while s of xy states that x squared is greater than y squared. So quite often, when it is clear from the context, the theorems are proved without explicitly using the laws of universal instantiation and universal generalization.